Hello, my name is Dan Ampray from Full Spectrum Diagnostics. Today we're going to look at the vibration fault periodic table. The periodic table is a logical visual mapping system to understanding vibration more as systems thinking. If we start with the full table, there's 35 common rotating machinery faults. Our first step is to logically sort these faults for frequency content. This means we define how the fault relates to shaft rotating speed. If the dominant response is at turning speed of the shaft, our fault is synchronous. If the dominant response is an exact multiple of shaft speed, our fault is harmonic. If the dominant peak is less than shaft speed, our response is subsynchronous. And if the peak is not an exact multiple of shaft speed, we have a non-synchronous problem. And finally, if the peak is pulsating, it might be due to frequency or amplitude modulation. Our second sorting mechanism is the dominant directional response. Red blocks on the table indicate a radial fault, yellow blocks indicate an axial fault, and orange blocks can be radial or axial. And finally, we perform a diagnostic test that's indicated in the upper right-hand corner of each block. Our tests are phase analysis, time waveform analysis, orbit analysis, transient analysis, and ultrasonic analysis. Okay, these tests will either confirm or refute the root cause or the problem. So let's get started. Our machine for this example is a centrifugal compressor, and we have our measurement positions P1, 2, 3, and 4. We want to take data at that bearing location in the axial, horizontal, and vertical directions. A little machine-specific information: it's an overhung centrifugal compressor. It has a 4-pole AC induction motor with no variable frequency drive. Its turning speed is 1784. The motor has rolling element bearings, the compressor has rolling element bearings, and the compressor has 24 blades. We're going to take a look at our data. So we'll go out with our assigned route data. We'll take measurements at positions 1, 2, 3, and 4 in the axial, horizontal, and vertical directions. So we should have at least 12 measurements. Okay. We're going to bring our route data back into the office. We're going to dump it to our computer database, which has all the alarm profiles. And the red line here that you see, the stair-stepped version of an alarm profile, is what we'll be comparing the peaks in our spectrum to. Okay, so we take a look. Axial looks like it has no alarm bands that have been violated, but the horizontal and vertical look like there's something going on at position 2. So this is the motor inboard side bearing location, and the rest of the machine looks fine. So there's something on the position 2 on the motor in the horizontal and vertical directions. Now we got a strange cluster of peaks, and it'll become more apparent what that is in a moment. Okay, we have rotating speed is 1784. We have alarm frequencies at 42,752, 49,952, 57,152. If we look at these individually, I can take that first one, 42,752, divide it by 1784, I get 23.964. So it's a non-synchronous ratio. If I look at 49,952 divided by 1784, I get exactly 28 times running speed. We're on a motor. There's no gearbox that can produce something like this because we just don't have one for this compressor. We might have blades in the compressor that might be able to, if we had 28 compressor blades. But the more logical one would be we have a rotor bar issue. We have 28 rotor bars in this motor. The third frequency, 57,152, divided by running speed, we have 32.035. It's a non-synchronous fault. Okay, now the question is, what is this gap? What is this sideband set? And if we go through and we have 28 minus 23.964, that'll tell us the fraction of running speed that this fault is giving us, what the sideband values are. In this case, it's plus or minus 7,200 CPM. 7,200 CPM is the electrical pulsation of the motor. It's 2 times line frequency. It's the polarity where you change and you're constantly reversing the magnetic field. And that's pretty much giveaway that it's an electrical problem in the motor. But we're going to have to refute all the other possibilities, and we'll get to that in a moment. For this, modulation faults has a little different profile than other groups. The actual modulation faults, you can have a ball spin frequency that has cage sidebands. You can have an inner race defect on a rolling element bearing, and it'll have 1 times RPM modulation. You can have barring in a paper plant, and obviously we don't have a paper plant here, so this isn't going to be one of the problems. And we can have natural frequencies that have 1 times RPM sidebands and fluting problems in the machine that have a little strange combination. They're a non-synchronous sideband, but they're the sideband at ball spin or inner race or outer race. So it's a special type. Now we have these boxes down here that are white, essentially. They're saying that we have a problem that's occurring here. Let's say a cage frequency in the bearing. It's also occurring here. So it's a non-synchronous peak, but it's a modulation problem. Okay, especially if it's sidebands at cage frequency. We have an electrical pole pass frequency, and that can show up as pole pass modulation. So there's a fault and a modulation fault. Here's a fault in a bearing and a modulation fault as well. Rotor bar, an electrical fault in a motor, so we have rotor bar passing frequency, and we have pulsations that create sidebands. And same thing with gear hunting tooth, and you see the combinations that can be looked at there. So sideband indicates a modulation fault. We definitely have some sidebands at 7,200, and we're going to refute everything that isn't rotor bar. So it's pretty likely it's rotor bar, but let's make sure. Directional grouping. There's horizontal vibration, usually shows up with electrical type pulsations. But you can't really eliminate anything based on those types of faults. Cage frequency is way too low a frequency, so it can't be the problem. It's at fractions, a little less than half of running speed. Instead, we have something out at 28 times running speed. It's not a barring fault. It's not a specialty machine we're looking at. There's no gearbox, so there's no hunting tooth signature. There's no pole pass. It is a pole pass frequency is a sideband on 7,200. It's nowhere near the 28 times running speed sideband that we're looking for. So we've taken a few things away. We have a rotor bar fault. We have ball spin, inner race defects, bearing natural frequency, and fluting. Okay, so we can take a peek at what each one of those faults is asking us for. So let's do the ultrasonic, because that's pretty much all the faults, and if we get rid of all those, we know what our root cause is. So we're going to look at the ultrasonics for these 4 bearing conditions. Random noise floor, that doesn't tell us anything about the frequency, so it's not a lubrication issue. Mechanical nuisance type C is 1 times RPM harmonics, and that's not something that we have for these faults. Rolling element bearing faults, there's nothing that shows up in the spectrum that applies to this. The one thing that does show up in the ultrasonic range is a non-synchronous frequency at 7,200 CPM and multiples of that. So 2 times line frequency, this high frequency pulsation is usually high enough that it'll start to be picked up by the ultrasonic spectrum. So it's very possible that it's an electrical fault. We didn't see any rolling element defect frequencies, so that's a key indicator that the ball spin and the inner race aren't there. And we didn't see any non-synchronous frequency out there that could be surrounded by 1 times RPM harmonics like the bearing natural frequency would be. And we didn't see any fluting sidebands. So the only thing that applies here is the electrical signature. And we're going to take a look at that. So diagnostic formats for modulation. We have a modulation checklist, and that check for rotor bar faults, and we have this signature. We have rotor bar passing frequency at 28 times running speed. We have 2 times line frequency sideband. So we're 99% sure this is the fault. Okay, here's our rotor bar. Here's what the signature looks like. It's a higher frequency signature. We check pole passing modulation. Pole passing is a lower frequency. It's 2 times line pole pass frequency is around 2 times line frequency as a sideband. Much too low for our application. Check for gear mesh modulation faults, and 1 times RPM sidebands around gear mesh frequency for the drive and the driven gear are common, just due to a little discrepancy in the cuts of the teeth on a gear. But we don't have 1 times RPM sideband, so that one doesn't jive. Check for hunting tooth modulations. They're very low frequency, tight sidebands that don't apply in this case. Check for rolling element bearing inner race modulation faults. This would produce a ball pass frequency inner plus or minus 1 times RPM, which we don't have. So we're not seeing that non-synchronous peak or those sidebands. Same thing with cage. The cage frequency would be very low for this type of fault. The last one is a check for fluting modulation faults. This would be a fluting center frequency that's non-synchronous and have plus or minus outer race, inner race, or ball spin sidebands. And we don't see any of those. So we are very confident that electrical rotor bar is our fault mechanism. Okay, and just as a note, we shouldn't go out and change the motor or do anything to it until we see changes in amplitude. It's very common to see this pulsation event going on, but the amplitudes tell us if there's actually a fault. And there we have it. We've sorted by frequency grouping, and we're a modulation type event going on. We sort by dominant directional groupings, and orange, radial or axial, didn't really have a bearing on what this fault would be. We did performed recommended diagnostics. We did our ultrasonic, and we came up with rotor bar being the most likely fault, logically sorted to probable root cause.